What we're going to do is take a trip to the Galactic Center, and the center of our galaxy is actually towards the constellation of Sagittarius, which is, I'm not even sure if it's very visible anymore in the nighttime sky. But it's if you know about the constellation of Sagittarius, I like to think of it as a teapot, and the center of the galaxy is actually just off the tip of the spout of the teapot. And if you zoom in with the Hubble Space Telescope, and there's a lot of obscuring gas and dust between us and the galactic center. It's about 26,000 light years away, and so you ordinarily can't really see very much with invisible light. You have to go into the infrared, and so here is the galactic center in infrared light. That's what all these stars are. We're seeing stars in the infrared, but superimposed on this blue is X-ray emission from observations from the Chandra Space Telescope, and we think we have very good evidence to suggest that there is a supermassive black hole at the very center of our galaxy. And the reason why we think this is that we have been mapping stars at the very center in the infrared. There have been a couple groups that have been doing this. One of them is Andrea Gheza's team at UCLA, and they've been doing this since about 1994. And so this plus mark marks the location of where we think the black hole is, and we can see the stars are orbiting around this point, even though we can't actually see anything at that point. But based on the information from mapping these stars and figuring out what their orbits are, we gather that there's probably about 4 million solar masses of material in that black hole. So we're seeing about 10 years worth of data, but we have about 20 years worth of data now. Here's yet another series of animations showing what the solar motions at the Galactic Center is like with the Keck telescope in Hawaii, using adaptive optics and then next generation adaptive optics. And then this is a simulation of what the extremely large telescope, which is currently under construction, the type of seeing that it will allow. So what we're hoping to do is to really map the essential stars and to understand things that might fall into the black hole. But in order to even see these stars are really massive stars. So they're usually at least 10 times the mass of our sun, and that allows them to be bright enough for us to observe them at this distance from the galactic center. But this also poses a really big question because massive stars like this live for a very short amount of time, meaning you don't expect, based on what we know about star formation, you don't expect star forming clouds to be close to the center of our galaxy, very close to a black hole, because these clouds would tend to get ripped apart by the tides from the black hole. But we do see dense clusters of stars close to the black hole, and so the question that still sort of puzzles astronomers is how did these stars end up around that central black hole? And the name of that central black hole is Sagittarius star A star. That's what that means. And the two leading theories or hypotheses is that the stars actually originated from a gas cloud that was in orbit around the black hole, and so the physics, the conditions for this cloud allows it to escape being torn apart. But while it was in orbit, parts of the cloud became unstable and collapsed to form these stars. The second possibility is that the cloud was actually further away, and so the stars formed much further away, and through dynamic processes, the stars ended up migrating in. So that's what this paper, one of the conclusions was for this particular paper was to figure out which one of these models is correct. And what they did was to map the stars at the galactic center in the space immediately around the black hole very accurately using a new instrument at the Very Large Telescope. That's actually the name of the telescope. It's down in Chile, and it's run by the European Southern Observatory. And what they find is that they detected close to 100 massive stars. That's what these OB stars are, including 20. They found 24 new ones. And when they looked at not just those stars, but also using models to determine how big this cluster must be, they have a minimum mass of at least 12,000 times the mass of our sun. And some of the other numbers in the paper, depending on what choices you use in your models, it could be up to 24 or even 30,000 solar masses. And then finally, what they also find is that this star cluster has an edge at about half a parsec out from the center of where the black hole is. And so if you map the star counts, and these red dots are from a previous paper, but these black dots are from the current paper. So what they're finding is that they're finding lots of stars in the very center of the cluster, and because their instrument allowed them to see a larger region and was also sensitive enough to see more stars, they were also able to find stars further out, out to about just around 1 parsec away from the black hole. And so they're finding kind of a very sharp cutoff for this cluster. And what this means is that this is actually evidence for the star cluster having formed in situ, or basically at the location of the black hole, as opposed to having migrated in. And the reason why is that if the star cluster formed much further out and migrated in due to interactions, gravitational interactions with other stars, it would actually leave a trail of stars, sort of like breadcrumbs. And so you would actually expect the points in this plot to sort of continue like following these red points here, but the fact that they drop down means that this cluster probably could not have migrated, because you would have seen more stars out here than what's shown. Somewhat, maybe not completely surprising result, but a lot of the previous results have actually lent support to the idea of a cluster that has migrated. But the fact that this new instrument allowed them to sensitively and to also get spectra of all these stars much further away allows them to make this somewhat very different conclusion. And so this shows you how astronomy, like a lot of other sciences, really depends on better and improved observations, not only in this particular work, but the previous one that I talked about as well.